All right. Let's get started, please. I did, as you may have noticed, purposely did not tell you about the derivatives of secant and cosecant, tangent and cotangent, so that you could look back in the section to find those. Did you notice that? Or did you just do the product quotient rule? Now, I didn't purposely not tell you that, but I did tell you. So, if you want to look up here, all right, these would be 4 more to add to our list of rules. They were, like I said, they were in the back. So if you got the one that was tangent of x, for example, you're supposed to do the tangent. You say, well, we don't know how to do the tangent, but maybe since it's in the homework, maybe we're supposed to be able to do the derivative tangent. So if you flip back a couple of pages, they're listed there. But if we had a shortened period yesterday, we would kind of just ran out of time, and I failed to mention those. So the derivative of tangent x is secant squared x. Derivative of tangent is secant squared. And that's one you just, all these we have to memorize. But that's just one you have to, that kind of out of thin air, derivative of tangent is secant squared. But if you can remember that, then cotangent is pretty easy. It's negative cosecant squared. Negative cosecant squared. And then you start to see a pattern a little bit. Remember, derivative of sine was cosine, but the derivative of cosine is negative sine. It's negative. Cosine, cosecant, and cotangent are called the cofunctions of the 6 trig functions. There's sine, there's tangent, and there's secant, and then there's their cofunctions, which are cosine, cotangent, and cosecant. And the cofunctions are all the ones that are negative. So derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. And then the last two, the derivative of secant is secant x times tangent x. And its cofunction, cosecant, its derivative is negative cosecant cotangent. So there definitely are some things there, some patterns there that you can use to help you to memorize those. All right? Now, over on the right here, you don't need to write this part down, but over here on the right, I've got the reason that tangent is secant squared. And it comes from the quotient rule. And that's one of the reasons we didn't learn about it in that earlier section on trig functions in chapter 2. If we write tangent as sine over cosine, and some of you went ahead and did these as when you ran into tangent. I saw it in some papers where you ran into tangent, you wrote it sine over cosine, did your quotient rule. That's great. That's because if that's all you knew, that's what you do. Okay? So I should write that down. Remember that. Sine over cosine. So, according to, go back to this page here, according to the quotient rule, u prime v minus uv prime over v squared. In other words, we take turns starting with the top first, derivative of the top, bottom left alone, and so forth. So we start here, derivative of the top. Now, there are several things I will be pointing out as we go through the next several days that are the common mistakes that people make. And we talk about this gateway test we have to take. We got to get 8 out of 10 to get a grade on it, unless you want to take your, to get a scaled grade, let's say. You get 8 or better, you get 30 out of 30. You do it one of the next couple times, you get 8 out of 10, you get 28 out of 30. Otherwise, you're just going to take whatever you get. 2 out of 10, that's a 6 out of 30. Okay? There are a lot of different little mistakes people make. Obviously, if you don't know the derivative rules, that's going to be a problem. But even if you do know the derivative rules, there's a lot of algebra. Some of you have already come and talked to me about this, about the algebra things that you have to be able to do in these problems. One of the biggest mistakes people make is right here. Derivative of sine, of course, is cosine. You leave the bottom alone, the cosine. Then the quotient rule says you got to subtract. Then you leave the top alone, which is sine. Okay? Then you do the derivative of the bottom, which is negative sine. Now, you got to really be careful with these negatives. I put a times sign there. Okay? And I put parentheses right here. That's really important because I'm subtracting this whole quantity. And this minus sign in the quotient rule gets us in a lot of trouble because we forget to distribute and we forget to do these various things. Okay? Now, on this one, you end up with, and of course, the bottom square. So cosine times cosine is cosine squared. Here we get sine times negative sine, which would be negative sine squared, but then we're subtracting it, so it turns to a positive. What's cosine squared plus sine squared? 1. 1 over cosine squared, of course, is secant squared. So if you ever can't remember this, you can certainly do a quotient rule, but you would want to go through all that work, when you could just memorize what it is. Okay? So those are the other 4 trig function derivative rules. We're developing quite a list of rules here that we got to know. All right. Next thing I want to look at is number 42, please. Number 42. Filling in this table. Now, there were a few things lacking that I noticed in the homework. One was 42, one was number 79. Okay? So I want to talk about those, and then I'll let you, see which ones you would like to see me work here. But on 42, to fill in the table, they gave you h of x was equal to f times g. I think I got that right. Is that what h was? Right? And then what was the other one? J? J of x was f divided by g. All right, so all you were supposed to do was take h prime, which is the product rule, and then likewise for j, do the quotient rule. And then to fill in the table at -2 for h, I think that's the first one you were supposed to fill in, was h prime of -2. That first empty box in the table. You simply put a -2 in all of these spots for x. And now all of those just come right out of the table. So f prime of -2 there is -1. G of -2 is -3. F of -2 was 1. And G prime of -2 was 4. And so you get 3 plus 4 or 7, and that would go in that spot in the table. Okay? So, that is not going to be on our gateway test. Now, okay, I don't want to minimize these problems. I mean, the gateway test, like I said yesterday, is more like that 9 through 41 odd. Here's a function, do the derivative. Here's a function, do the derivative. But this whole purpose of Chapter 3 is to be able to do these derivatives, so when we get to Chapter 4, we're really going to come back and revisit a lot of the stuff from Chapter 2. Max, min, chart questions, stuff like that. So along the way, we're going to keep doing them. Okay? You really can kind of think of Chapter 3, the way they've organized this book is this way. We learned about the chart, we learned about all the connections between f, f prime, f double prime. There really are no more new connections to learn. And then we started with some basic derivatives and said, okay, now let's do some problems that involve the chart and max, min, and all that stuff. And then we did that, and that was Chapter 2. Then they say, but there's a lot more derivatives out there. So let's take Chapter 3 to learn about all these more complex derivatives, and then we come back in Chapter 4 and we say, all right, now let's go do the stuff we did in Chapter 2, but with harder equations. More difficult functions, more complex type derivatives. And okay, so we need to keep doing that stuff along the way. And questions like this are favorite ones for the AP test too, so like for our midterm and things like that, to be able to work these various derivative kind of things in them. All right, let's go to number 79. All right, oops. Now, on number 79, this is kind of what I'm talking about here. they give us a function that until yesterday we could not have done the derivative of. So we would have no way of finding the stationary points, and we would have no way of finding max and min or inflection points or any of that other stuff. Okay? Well, now we do. So there's nothing new in number 79 that we haven't already been doing. Okay? They want to find the max value, the min value, and the inflection point. Well, we start by doing the derivative. Well, there's what your derivative should look like. Derivative of the first is e to the x. We leave the cosine x alone. Plus, we leave the e to the x alone. Derivative of cosine is negative sine. Now, again, I see this all the time. I will guarantee you, I hope I'm wrong, but on the gateway test for this problem, uh-oh, I was going to be recording this. I am recording this. So I should switch. Not sure how to do this. Yeah, everybody close your eyes. Quick. All right. I promise that somebody on the gateway test for this derivative, and what was it, e to the x times cosine x? Is that it? Is going to do this. You're going to write down, you're going to say, okay, derivative of the first is e to the x. We leave the cosine x alone. Minus, then we leave the e to the x alone, and then we do the derivative of cosine, which is negative sine x. And you're going to write it just like that. And then you're going to get it wrong, right? Because it's not a subtraction. That's what that looks like, right? What you meant was like to have a big times sign there, right? Oh, this is a product. You're right. Okay, I'm sorry. You okay?
Yeah, you're okay. I was like,
Like chemistry will do that to you. Is that what you're working on?
Yeah.
Chemistry? Is that chemistry? Is that what? Sometimes that will make you sick. I think it's the guilt of working on chemistry and calculus class. So, okay, well now I kind of ruined that because I messed it up with my minus sign. Okay, it should have been a plus sign. So that I'm not guaranteeing anybody will do that. But what people are going to do is when you get to this point where you have to do the derivative of cosine, okay, you're going to write negative sine and you're going to write it like that. Okay? Now that's correct if you put parentheses around. That's okay. But if you write it without the parentheses, that means what you wrote would subtract. Now I know what you were thinking, but that's not what you said. Okay? And I'm grading what you said, not what you were thinking. Okay? So you've got to make sure you do that right. Now, what should probably end up then is you should end up writing e to the x cosine x minus e to the x sine x. That's the best way to then write it. So these little things with negatives and with the algebra stuff are killers. Alright? And so you got to be careful of that. You don't have a lot of room for error on these. Alright, so back to this. So, there is the derivative. I'm going to set it equal to 0. Now what can we do to solve this? Factor out an e to the x. Then we get this. Now, once we factor out, we can set each one of them equal to 0. Okay? Now, when does e to the x equal 0?
Never.
E to the x looks like this. It never crosses the x-axis. It's never 0. Okay? So, empty set there. Now, how do we solve this? Well, there'll be several ways to solve this. One way would be to add the sine x over here and do cosine x equals sine x. Now, my favorite way on this one to solve it is just actually to stop there and just ask yourself, when does cosine x equal sine x? When on the unit circle, since cosine and sine are the x and the y coordinates, are they equal? And that's at pi 4, so on a 45-degree triangle. And over here, the x coordinate's negative and the y coordinate's positive, so it wouldn't be there. Okay, and we're only supposed to look from 0 to pi. Now what if this was 0 to 2 pi? Then we'd be down here where they're both negative. We'd be at 5 pi 4. Okay, so that's the quickest and fastest way to do it. Now if you want to look at another way to do it, would be to divide both sides by cosine x. But you always get in trouble when you, or potential trouble when you divide by an x, because you can't divide by 0. So anytime you divide by something that's got an x in it, you got to be careful to say, well, when is that 0? And I might be losing a potential solution. So when is cosine 0? Well, that'd be a pi halves or 3 pi halves. Well, it turns out those wouldn't work here anyway. Okay? So it ends up okay. So you end up with 1 equals tangent x. Well, now that's that same question. When does tangent x equal 1? Well, that's at pi 4s. So either way, but that's your only stationary point. So now, what are we going to do? Are we going to do a number line on this one or a list of candidates? What's it say? It asks for a max and a min value. That's global. That's list of candidates. So you would need to then go and plug into the original 0. So you'd want to do f of 0, f of pi, and f of pi 4s. Okay? So that's for parts A and B. For part C, let's see, yes. Okay, for part C it wanted inflection points. What do you need for inflection points? Second derivative. Well, here was f prime. How are we going to do f double prime?
Separate things.
You could factor out an e, then you'd have just an e to the x times a thing, and you'd have one product rule. As opposed to this, the way I have it written now, I've got to do 2 product rules. Now, if I factor out an e, I'll have 1 product rule, but I think it'll be more difficult.
Hey. I think my mom's
All right. Now, I would, and that's a great point because I think I mentioned this yesterday. The algebra is a very big part of this. Sometimes you have a function that you can do some algebra to first, might make the derivative easier. Sometimes, though, it actually makes the derivative harder. Okay? So what you want to do is you want to look at something and say, is there some algebra I can do that will make my life easier? Then I should do it. In this case, I think it's probably about 6 of one, half dozen of the other. I'm not sure it matters. Cosine x minus sine x. Now you can do your product rule, but then you got a little more complicated one on the second part. Let's just take a look at both ways. So here, the derivative of the first e to the x, leave the cosine x alone. Actually, we know this one, right? It's the derivative of this first part is what we've already done. It's this thing. So it's e to the x, so that can simplify my life a little bit. So I just did that part right there. Now, where we sometimes get in trouble too then is with this minus. I usually put a minus and then a big set of parentheses. Because what I know I'm doing here is I got a minus and now I'm about to do that derivative. So I don't forget about that minus, I could do this. Okay? Now, to be honest, probably the better strategy though, and this is what I would encourage you to do, is think like I tell my freshman algebra 1A kids. I would think of this as that'll add the opposite thing, and I would attach that negative to the e to the x. And then, now here's my 2 products, but if that negative is part of the first piece, I won't lose it, okay? The same thing is true of, it's just like if you have negative 2x. You can think of that as 2x with a negative on it, or you can think of it as negative 2 times x. And the better one is to do negative 2 times x.
gotta see. It's better be important. Okay. Money.
Wow.
I think you got things that David.
All right. All right. So, okay, when you've got 2 things multiplied together and there's a minus in front of it, you're going to have to do a product or a quotient rule. Stick the negative on the first term, and then you don't have to worry about distributing it through or forgetting about it. So in this case, I would say, all right, the derivative of the first is negative e to the x with the sine x left alone, and then the first left alone would be negative e to the x, and then the derivative of that is cosine. So that way you don't have to think about distributing it, it just comes along as part of that first factor. Okay?
Yeah.
That's a good way to do it. All right, now a few nice things happen here, so it's not as bad as it looks. Those cancel out, and we end up getting negative 2 e to the x sine x. Okay? Equals 0. I think I did that right, didn't I? Okay, I think that's right. So now this part here will never equal 0. So the only place we have to look is where sine x equals 0. And that's at what? 0 and pi. Okay? Now that's interesting. Those are the endpoints, aren't they?
Yeah.
Everybody look up in the back what they say for inflection points. Was this in the back? Everybody look? They didn't put a C?
They didn't know how to
They didn't know how to do it either. They gave up after a while. Okay? Well, I would say no inflection points. I'm just curious if they said, yeah, they said at 0 and pi, but for us, and on the AP test, they don't get into that. They won't give you one where it's endpoints. So I would say we would say no endpoints. We could make a number line and we could check on the other side. It's not like there aren't other values there, but it's not in our domain. So it turns out they are inflection points if you look on the other side. We're typically going to say we're not going to call local maxes mins or inflection points at the endpoints. We're not going to check those. So for us, we would say no inflection points. All right. So now, your questions. Let me see if that's everything. I think that's it. All right. So which ones would you like to talk about? Whether it was, what the answer in the back looked like, because I really do want you to look these up and see and match. And a few of you will come in and ask me about the fact that they simplified them in the back and look differently than what you had done. And maybe, and of course what I was saying yesterday is type into your calculator as a check too. But now the calculator is going to simplify things also. And it may not simplify it quite like you did. So even if you think you got the right answer, but you want to talk about that simplifying part of it, we can do that too. Anybody have any that they want to see?
35.
Which one?
35.
35. Okay. F of x equals,
Wait, that's easier with the new.
it is easy now with the new rules, but you know what? I've already got it written, so what the heck. So with, and this is another thing with the trig ones that you have to get out of the habit of a little bit, is, and I do the same thing when I say like sine squared plus cosine squared equals 1. But we got to remember that sine of x squared plus cosine of x squared equals 1. And so when we say the derivative of cosecant is negative cosecant cotangent, we always remember there's that input x as part of the function. Well, there's a couple things we learned last chapter that still are true. When you have a 3 sitting out in front, what do you do with it? You leave it there.
Can we do this one without the renewal?
Just to check it?
Yeah.
Sure.
So we can see it.
Yep. So let's finish it with the new rule. So we got 3. Now again, I'm going to put parentheses because I know this is going to get messy here, and they may not end up mattering, but I'm going to put them there. So the derivative of cosecant we said is negative cosecant cotangent. Now I didn't say the inputs again, but what did we say about the inside? Stays the same. So you're always going to keep the 2x in there. So it's going to be negative cosecant 2x cotangent 2x. Right? And then also we have to do what?
Kick out the 2.
Kick out the 2. So we end up with this. Now looking at it, it turns out that it's all multiplication. There is no addition or subtraction. That's when we got to be careful. So the parentheses I don't really need. So the 2 and the 3 I should put together with the negative to make negative 6 cosecant 2x cotangent 2x. That's my final answer there. Now, when you say you did it without the new rule, you wrote it as 3 over sine 2x, okay? So, if you do that, now, I would, because of the new rules we have and so forth, generally I would say, if you've got a constant in either the top or the bottom, that's all you have is just a constant, then I would usually stay away from the quotient rule. It works, but there are some places you can make mistakes, and number one, it's longer, and number two, but if you can't think of anything else, do it, but number two, there are some potential mistakes that people seem to always make. All right? Now, and what I mean by that is, let's say I had sine x over 4, and I was supposed to do that derivative. I would not think of the quotient rule there. I would rewrite it as what? 1/4 sine x. That is much easier to do the derivative of than try to do a quotient rule. And you notice how throughout the year I've been telling you that in this class it's better to write it as this than this? Well, this is one of those reasons. Because when you write it like this, it looks like a quotient rule. And you just get in a lot of trouble there because that's such an easy derivative this way, right? It's 1/4 cosine x, and you're done. This way, thinking a quotient rule, it just makes it much harder. Okay? The same is true if I have a constant on top, as you just saw. It's easier to do it this way than what we're about to do with quotient rule. But here's what it would look like. So we would do the derivative of the top, right? What's the derivative? And this is the part we usually mess up. What's the derivative of 3? 0 times sine 2x left alone minus the top left alone times the derivative of the bottom, which is 2 cosine 2x, because you have to kick out the 2, right? All over the bottom square, right? So then we end up with, that's 0, so we end up with -6 cosine 2x all over sine squared 2x, right? Which is okay to leave. If I was doing this, if I had done this with my quotient rule, I would have left it like this. Okay? But feels like I'm missing something here.
You can do cosine over sine.
Oh yes, okay. So if I was to rewrite this as cosine 2x over sine 2x sine 2x, right? If I want to see where this one came from, okay? Probably been easier to rewrite this one, but either way it's going to work. And then this would be the same as writing -6 cosine 2x over sine 2x. These are just algebra things I'm doing right now. Right? I can split that apart because it's multiplied. When you multiply two fractions, you multiply the tops, multiply the bottoms. So this would still be the same thing. And then what is this? This is -6 cotangent, and this is cosecant, which is the same as that. But if you did it as a product, let's say on the gateway test, I would be looking at your work. If you stopped right here, you'd have been fine. If you did it with the shortcut, which I expect most of us will do, you would have stopped right there. But they are the same. And this is where it's hard to check in the back of the book, because I'm guessing the back of the book would have said this. Yeah. Okay. And it's also hard on your calculator. Did anybody do the calculator? Try the calculator. Try on the calculator and see what it says. It says this one. It says this one. See, because I think what the calculator tries to do is turn everything into sines and cosines. I think the calculator tries to turn everything into sines and cosines. What you would want to do, I think I said this earlier, but let me say it again. This is important. If you're using your calculator as a check, you type this in, tell it to do the derivative, and it gives you this. You, on your paper, had worked it out and got this. Type your answer into the calculator also then. If you type, try this for me, somebody. Type this into the calculator and just hit enter. This isn't always gonna work, but on our old calculators, it worked quite a bit, and this is pretty much the same software, so I think it's gonna still work. Type in negative 6 cosecant 2x cotangent 2x and hit enter and see if it doesn't do this. Does it write this? So you see what I'm saying? So you told the calculator to do the derivative, it gave you this. Your answer was this, so type your answer in and hit enter and see if it matches. And if it matches, then you know yours was right. So that's a way you can check. All right. What else? For some reason, we mess up that zero part. You know, when you do the derivative of the 3, which is 0, and then it wipes out stuff, and we mess that up. Okay,
31.
31. We've got x plus 1 squared over x squared plus 1. So the question would be, is there any algebra you could do to make it simpler? And I would say the answer is no. I mean, if you could factor and cancel some things, that'd be fine. But I don't think foiling out the top is gonna help us any. Now, let me show you one where it would work to do that. If you had something like x plus 1 squared and the bottom was just x squared. So that would be a very small change in the problem. But in this one, I think you'd be better off to do a little bit of algebra. Now, not much better off, not a whole lot better off necessarily. But whenever you have a single denominator like this, what can we do? We could split it into 3 separate fractions, right? It's legal. I mean, you could bring this up and distribute. I think that's more difficult. You're going to hear a lot this year where I say split apart the fraction, right? Now, you can only split apart a single denominator, right? Because to add it back together, you have to have common denominators. But this simplifies to 1. This would be 2 over x, which is this. And this would just be x to the negative 2. Now, that's pretty easy to do the derivative of. Of course, one of the problems is we forget, and we think this is our answer. We forget that we were just simplifying. This is still f of x here, right? Now I have to do f prime. So that'd be 0, that'd be negative 2x to the negative 2. This would be negative 2x to the negative 3, and it'd be done. So it depends. Did you like the algebra better and then have a simple derivative, or would you rather go through a quotient rule? Okay, on this one, I don't think there'd be any algebra that would benefit us. Okay, so let's run through it. The derivative of the top, the u prime derivative of the top would be what? 2 x plus 1 to the first, and there's nothing we have to kick out, times the bottom left alone, minus the top left alone, times the derivative of the bottom, which is 2x. Since it's just one term, I don't need parentheses right now. All over x squared plus 1 squared. Did I do that right? Okay. So now the question is, am I done? Can I stop? The rule for algebra simplifying is if you can factor it and cancel or combine some terms, then you should do that. But if you're just rearranging things, that's not necessary. Okay? Now I was first thinking I could, because I've got x squared plus 1's down here, if I could factor an x squared plus 1 out of both of these, but I can't, right? This one doesn't have an x squared plus 1, it has an x plus 1. This has an x plus 1. I could take an x plus 1 out, I could take a 2 out, but none of those would cancel with anything down here. See what I mean? So any factoring I do on top would mostly just be rearranging stuff. So it would be unnecessary. So you could stop here.
Yes.
What's it have in the back?
It has -2 declining x squared minus 1 over declining x squared plus 1 squared.
Oh, because there must be some things that,
It has the FOIL.
oh, right here.
And then
If we take out the 2 and the x plus 1. Now, with this said, and we will have this discussion a lot over the next several days as we're getting ready for the thing. It's about the simplifying. And you'll get a hang of it more as we go through it. There will be, out of 10, probably a few, 2, maybe 3 at the most, that need very much simplifying. Okay, so I'm mostly interested in your ability to do the derivatives. So I'm mostly interested in your ability to get to here. Now, remember what I said about our next goal, though, is once we learn these derivatives, that we can go back and do the max, min problems, inflection point problems, all those very important problems. And those all involve doing the derivative and setting it equal to 0. Well, if I'm going to do this derivative and now I'm going to solve it, now we definitely have to do some simplifying, some factoring and stuff, because that's the only way you're going to set this equal to 0 and be able to solve it. Okay? So we definitely are going to have to be able to do it. But for the gateway test, my guess is, even on this one, you might get away with stopping right there. Now, I think you're right. If I take out a 2 and an x plus 1, we'd end up with an x squared plus 1. I took out the 2, so that would leave me an x and x plus 1, right? And so we'd end up with this. Now this ends up being x squared plus 1 minus x squared minus 1, right? Minus x, 1x, right. And the x squareds drop out. So we end up with 2x plus 1, 1 minus x, all over x squared plus 1 squared. Is that what you said it was here? Did they FOIL this out then to get, you said 1 minus x squared, or what?
It was -2
Ah.
declining x squared minus 1.
Okay, what they did is this 1 minus x, they pulled out a negative to make it x minus 1. Now to me, that's just rearranging. At that point, that's just rearranging stuff, and that's not that important. So one of the things I did say a minute ago was if you could combine some things, and what happened was the x squareds dropped out here. So that was it wasn't a lot, but a little bit happened there. Okay, so that would be a good answer. On the gateway test, I don't know. Fair chance that that could happen. That would have been good enough for you to stop there. Okay? A big part of getting 8 out of 10, I think one of the reasons that we don't have a higher percentage than maybe a third of the people get to 8 out of 10 is we don't practice enough. You don't practice enough of them because all of these little algebra things that happen to you, all of the little things about taking out a negative or making sure you don't lose it or whatever, those show up on the gateway test. A lot of people get 2 out of 10. Well, 4 of their problems were just little things. You know, just instead of sine, derivative cosine, they put negative cosine or something like that. So it doesn't sound too bad to get 8 out of 10, but it might be harder than you think. Or at least it takes a little more work than you might think.
Do you get to see what you did wrong?
Yeah, because I give you each one's a different one. So yeah, once we do the first one, I'll pass them back. We'll talk about it, and then each subsequent one, if you still aren't getting it, I let you look at it and see where you are. Absolutely. Okay, let's talk about our new rule for today. And then, because I want to give you some, practice time today here. Okay, this is called the chain rule. The chain rule. Now, the chain rule deals with composite functions. Composite functions are when you have one function inside of another. All right? of g of x. Now there are some different notations for composite functions. I call it I guess the fog notation or whatever, but you see it in the book. Sometimes they write this, and I have no earthly idea why they think that's better. But that also means f of g of x. All right? So if you see that in the book, that's what they're talking about. But we're going to talk a lot about outer function and inner function. And so some of your early homework, some of the early problems in the homework are just about composite functions. All right? For example, if I tell you that f of x is natural log x, and I tell you that g of x is x squared, right? Those are my two functions. Then the rules we learned yesterday, the product rule would say you'd have x squared times ln x. The quotient rule, you might have x squared divided by ln x. But for a composite function, you know, one is inside of the other. Well, you have two options. ln of x squared, right? That's one way you could do that. Now, what would that be using f and g? F would be the outer function, natural log, and x squared would be the inner function, so that'd be f of g of x. And likewise, what would g of f of x look like? ln of x squared. See, their squaring is the outer function, and natural log is the inner function. So natural log is inside of the square function. Think of it as this. Think of it this way. When we talk about the natural log function, we say natural log of something. When we talk about the squaring function, we usually call it the squaring function, but that's really what it is. We say it's something squared. Okay? So there will be some homework problems where they just have you write f of g and g of f and make sure you understand which one's the inside function, which one's the outer function. We've already done some of this. All right? When we do... let's take a look at the calculator here. Go ahead and get your calculator out. Let's look at that. If you let's do the derivative, for example. Oops. Let's do the derivative of e to the 2x. Okay, now what is that going to be? 2e to the 2x. We kick out the 2. So, but that was a function inside of a function. 2x is a function. And it's inside the e function. So we kicked out a 2. So if we would do the derivative of... let's say we did sine, and then we did 4 minus x on the inside. Now, what would we expect to have to kick out there?
4.
A -1. We've always said it's whatever's multiplied inside by the x. And, of course, we'd still have cosine, and the inside, we've always said, stays the same. So we get cosine of 4 minus x, and we'd have to kick out a negative. Oh,
What the heck?
why'd they switch it to x minus 4? Because it's an even, right?
Yeah.
Listen, let me type in, just watch this. If I type in cosine 4 minus x, just type in cosine 4 minus x and hit enter, it writes it cosine x minus 4. Because one of the things it's programmed to do, whenever it has a polynomial like that binomial there, x minus 4, it wants to write it in order of decreasing power. So it wants to write the highest power first. So it wants to write as an x. So what it does, it uses the fact cosine's an even function. And remember what that means. If cosine's an even function, then that means that cosine of, when you put opposites in, When you put opposites in, you get the same thing out. Right? That's even function. 4 minus x and x minus 4 are opposites. Okay? If you take a negative out of 4 minus x, you get a negative 4 and a positive x, and you get that. So cosine of x minus 4 is the same as cosine 4 minus x. So we said we'd have to kick out a negative. There's the negative right there. And so when you see that, and that's going to happen to you on some of these when you're checking your work, you might not even notice it. But if it's sine, which is an odd function, you should notice it because there won't be a negative on the outside, which you're expecting. Okay? Matter of fact, let's just do that. So if we did the derivative, let's do the derivative, with respect to x, and this time let's do cosine 4 minus x, and hit enter. And you'd be expecting the derivative of cosine is negative sine, but then you got to kick out a negative, so you'd be expecting it to be a positive sign, and it's not. Well, that's because it flipped that around, and since sine is an odd function, you get opposites out. So when you flip it around to x minus 4, you get the opposite of what you had. So again, that's something else you have to keep in mind when you're using your calculator to check. But again, just type your answer in. You're going to say, well, wait a minute. For my answer, I had positive sine of 4 minus x. That's what I had. You type it in. Oh, it's the same thing. Okay, so my answer is the same as what they said. All right. So we already know a little bit about what happens when you put a function inside of a function. You got to kick out. All right. So don't get ahead of me here. Big surprise at the end here. If I do sine of x squared, don't hit enter. Don't do it. What do we expect, or what do we think the answer might be? Just take a guess.
2x cosine x squared.
Well, first of all, there should be a cosine, for sure. And there should be a cosine x squared, because we always leave the inside alone. The problem is, what do we kick out? Why?
Because that's x.
Why 2x, Jacob?
I don't know. Just threw it out there because there's oh.
Because you didn't take computer.
He didn't. I looked.
You did.
He just deleted it.
He just deleted it. Did you delete it?
Yeah.
Listen. If you've got, let's think about the ones we just did a minute ago. You've got 2x in there. We had e to the 2x, right? And we kicked out the 2. Now, we said we kicked out the 2 because it compressed the graph and made the slope steeper by 2. Now, what's an x squared do to the graph? I have no idea. It's going to change it in all kinds of weird ways, not a constant way like the 2 would. So the 2, it did have to do with the slope and that 2. But also, think about 2x. What's the derivative of 2x? 2. Matter of fact, anytime you have just an x on the inside and there's a number in front of it, what's the derivative of it? Just that number that's in front. So all along when we were saying whatever number's in front of the x you got to kick out, what we were really saying is it's the derivative of what's on the inside that we kick out. And so Jacob is exactly right that when you hit enter, look what gets kicked out is a 2x. The derivative of the inside. The derivative of the x squared. So this will not change what we have been doing. It will just add to it. Okay? So every one of these, like right here, when I did the derivative of cosine, we say, well, the derivative of cosine is negative sine. We leave the inside alone, but we have to kick out the derivative of the inside. Well, if you think about the inside, 4 minus x, what's the derivative of 4? 0. Minus x, the derivative of negative x? Negative 1, right? So we kick out the negative 1. So all this is done is more formalized what we were doing before. As a matter of fact, to make it easier, because some of you still were fuzzy about that whole kicking out something. Now you've got something actually to hang on to. It's the derivative of the inside. All right, so we're gonna write it like this. Think about the order that we do it. It's really a three-step process. We do the derivative of the outside. We're gonna write this in words here in a minute. We do the derivative of the outer function. So on the cosine example there, or no, the last example, the sine example. Sine is the outer function. So it is important to be able to identify your outside and your inside functions. We do the derivative of the outside, which is sine. The derivative sine, excuse me, is cosine. What do we do with the inside? We leave it alone. So the g of x is untouched. So we do the derivative of the outside is f prime. We leave the g of x alone times
G prime.
g prime of x. That is the chain rule right there. In words it says derivative of the outside, that's step one. Leave the inside alone. Multiply, and it's important that you multiply by the derivative of the inside. That is the chain rule. F of g of x. You do the derivative of the outside, f prime, you leave the g of x alone, times g prime of x, the derivative of the inside. This greatly multiplies the number of possible functions that we can do. As a matter of fact, it pretty much completes our list of derivative rules, except for the inverse trig functions, the arcsines, arccosines, which we'll talk about tomorrow, and then one other technique that works on special types of equations that aren't functions that we'll have to talk about there. But otherwise, this greatly expands what we can do. So let's take a look at an example. So let's say f of x is okay. Let's say f of x is this function right here. Okay? What rule are we going to have to use to do this? Rule or rules, I guess. Product rule and chain rule. Because first and foremost, it's a product rule. Because we've got a u times a v. So that's what we have to deal with first, is the product rule. But in the midst of doing the product rule, right, and remember what the product rule says is u prime v plus uv prime, right? And in the midst of doing that product rule, right here, we're going to have to do u prime. And to do u prime, you're going to need the chain rule, right? So these rules do not exist alone, okay? You will do them in combination. So we start, so you have to recognize when you look at this one, okay, first and foremost, this is a product rule. So we start with the derivative of the first thing. Okay, so the derivative of the first thing we just did over there, right? It's
2x cosine x squared.
2x cosine x squared. Now you're going to get good enough, maybe on an easy one like this, you're good enough already, that you already think ahead to the last step, the multiply by the derivative of the inside. You're already thinking, hey, I'm going to kick out a 2x. And you put that in front, because that would be the best place to put it. Okay? But a lot of times, you'll first write it over here. Okay? Times what? The v left alone. Plus the first one left alone times 9x squared using the power rule on the v. Okay? Now, there are some things, there is some rearranging you should do. Like, for example, you got a 2 and a 3 that can multiply to make 6, and an x cubed and x. That's not really rearranging. That is combining some things, so you should do that. So here I would get 6x to the 4th cosine x squared. And then just moving that around is not a big deal, but since I'm doing the other stuff anyway, I'll go ahead and put the 9x squared around front. But then that's good enough. Okay? Yeah, you can take out a 3x squared, but it doesn't do anything for you. It doesn't allow you to cancel anything or anything like that. All right? And there is a plus sign in between those. All right. Let's take a look at this one. Okay? Let's try the quantity 4x squared plus natural log 3x all to the 4th power. Now, this one is first and foremost a chain rule because it's got an outer function, 4th power function with stuff on the inside. And the stuff on the inside, there's no product rule or quotient rule or anything. But there is another small chain rule here, right? I mean, but again, you just kick out a 3. I mean, it's not important that you, it's not like you have to say to yourself, chain rule, while I'm doing the chain rule, you know what I mean? At some point, you'll just do whatever needs to be done. So we'll start here with what? Start with what? Bring the 4 down in front. This is really power rule, isn't it? It's something to the 4th power. The outer function here is the 4th power function. If you had to write the outer function, you'd say this is x to the 4th. Okay, or something to the 4th. That's what this function is. All right, so we'll bring the 4 down in front. We always leave the inside alone. To the 3rd. Now here's another algebra mistake people are going to make. I promise. You're going to say times, right? And what do we got to do now? Derivative of the inside. So, what's the derivative of the inside? 8x plus, what's the derivative of ln 3x? Derivative of ln x is 1 over x, right? So this will be 1 over 3x times 3. That's the chain rule for that part. 3's do cancel. And this is terribly, terribly wrong. Parentheses. Because think about what we got to do. We got to do the derivative of the outside. We got to leave the inside alone, and then we have to multiply by the derivative of the inside. This whole thing is a derivative of the inside. What have I multiplied by here the way I wrote it?
8x.
Just the 8x. I have not multiplied by this whole thing. And I don't care how big you make that dot. You have still not multiplied by that whole thing. I see people do that. They make a great big dot. It doesn't matter. Okay? You've got to have parentheses. So, when you get to that 3rd step where you multiply by the derivative of the inside, you know, it's what you'll see me do most of the time is I'll write out the problem. And when I get to here, times by the, when I get to here, I'm going to multiply by the derivative of the inside. I just put a big set of parentheses first.
You underline the big inside, and then it was just
All right. I'll put a big set of parentheses to hold the derivative of the inside to make sure I don't forget about it. Because sometimes the inside derivative gets kind of messy, and it takes you a little while. And by the time you get done writing it out, you've forgotten that the whole thing needs to be in parentheses. All right. I kind of went off track. All right. One more of those, and then I want to show you one of kind of a max min situation or something like that. So if I've got, let's do this one. Timeout. Early. I just want you to hear that sound. All right. Okay, look at that one. Ooh. Okay.
That fact is
What's that?
that fact.
Oh. All right, so sine of e to the x over x squared. So when I go to do the derivative, first this is what? It's a quotient rule and a chain rule in there, but what am I doing first? Chain rule is first. You got an outside function, which is sine. You're going to leave the inside alone, and then you're going to do the derivative of the inside. And when you do the derivative of the inside, it's going to need the quotient rule. So it would be what? Cosine, leave the inside alone, times, and then big parentheses, big parentheses to hold the quotient rule. So I don't forget now, since it's one big fraction, it's probably not, the parentheses end up not mattering that much, but go ahead and do it. So the quotient rule says, derivative of the top is e to the x, leave the x squared alone, minus e to the x left alone, derivative of x, x squared is 2x. Right there, now if this was a more complex one, instead of an x squared on the bottom, if it had several terms, then I'd have needed a set of parentheses around that 2x in that region. That's, again, another place you can forget about the parentheses that might be necessary. And then on the bottom, x squared squared is x to the fourth. Now remember, when you have a power on a power, you multiply the powers. Power on a power, you multiply the power. So x squared squared, x to the fourth. Okay? Now, we can't cancel anything inside of the cosine. So don't try to do that. But there is something we could simplify here. Okay? We could take out, we could take out e to the x, but that wouldn't cancel with anything, so I probably wouldn't. You could, it wouldn't hurt anything. But I would take out an x because it can cancel there. See, we're used to taking out as much as we can, the greatest common factor, but usually what we do in these cases is just factor out as much as we can that will cancel. So take out an x, so we end up with e to the x times x minus 2e to the x over x cubed. And then over here we still have the cosine e to the x over x squared. There's your derivative. It's nice. You know, somebody asked me in their class about these 10 questions. How hard are the 10 questions? And I would say there's a mixture. I would say they go from kind of easy, which would mean just straight, which would mean the stuff we learned in chapter 2. Straight power rule, straight, kick out something. So there'll be a few of those. There'll be some medium. This one would this would be medium to almost hard maybe, because it's got some chain rule and a quotient rule mixed in. But all the functions were pretty easy. I mean, e to the x, it didn't have e to the 3x, or it did, so.
Can you give us an example of a hard one?
Well, we're getting to those. We haven't probably gotten to the really hard ones. But, all right. Turn in your book, please, to page 176. All right, let's look, this one's in your homework. This is number 32. I figure since I usually end up doing the last one on the homework anyway, I thought we'll just do it today before we even start. So how about that? So number 30, something about that last one. All right. Now I'll see if I've got. I don't think I do have pictures. So you've got the pictures. You've got the pictures at the bottom of page 176. Okay. At the bottom of page 176, you have the pictures that go for exercises 29 through 36. Okay. Graph of F, graph of G. So instead of getting an actual equation to work with, you've got graphs. So 32 says K of X is equal to G of F of X. And in parts A and B, it's going to ask you for some K values and some K prime values. So before you can do the K values, of course, you're going to have to do K prime. Or excuse me, before you can do the K prime values, you're going to have to know what K prime of X is. So how would I write K prime of X? G prime, leave F of X alone, times the derivative of the inside, F prime. That's just a basic chain rule. You got G with F inside, you do the derivative of the outside, which is G prime, leave the F of X alone, times the derivative inside F prime. So therefore, let's just do two of the examples. They said evaluate K of 0. So K of 0 means do G of F of 0. Right? K of 0 means put a 0 in for X. So how do I do G of F of 0? This is back to the old Algebra 2 stuff with composite functions. Where do I look first?
Find F of 0.
Go to the F graph. So I'm looking where 0 is an input on the F graph, and I get what for the output? Oh, shoot. That was easy. So that's okay. We get 0. Now the output, now this is important. So what that means, and this is what composite functions mean anyway, the output of the F graph is now the input for the G graph. So we go over to the G graph and look at 0, and we get 2. So it's just some practice going back and looking at those values. Now, let's jump to B where it says estimate K prime of 0. So K prime of 0 would be just putting a 0 in these places for X. Okay? So putting a 0 in all those places. So first we look up F of 0, which we just had done, which is 0. So now we end up, that ends, I would rewrite that, is probably useful. So we end up with G prime of 0 times F prime of 0. What's G prime of 0?
Negative.
So we're estimating. Notice the direction said estimate. We're looking at the tangent line on the graph now. Looks like it's steeper -1. Maybe -2. So G prime of 0 is about -2. What about F prime of 0?
0.
Oh, I should have done that one first. Oh well. I wouldn't have had to do the other one. But anyway, so we get 0 for that answer. But if we'd have gotten another estimated value, then we multiply them together and we get that approximation. So it's doing the same thing, still using the chain rule, but just looking at it from a little different perspective with graphs and so forth. Okay, definitely the types of questions we'll have, maybe in our midterm, maybe we get into chapter 4, some of that stuff. Have to be able to do with these derivatives all the stuff we've done in those earlier chapters. Just on this next test, this gateway test, this kind of stuff won't be on. Okay, it'll be more like the ones we were practicing here a little bit ago. All right, so your homework is that 3.2, so you can go ahead, you got about 15, a little more than 15 minutes to work. There'll be a little product rule stuff mixed in. Mostly it's a chain rule things. Get used to that.
Do you have the worksheet?
Yep. All right, so let's go ahead and work for a little while here.
Yeah. Work for a little while.
Good. David can get a little homework done.
Yeah.
are we doing tomorrow?
We're gonna go. Let me see.
And then
I think we are going to do section 3.3 tomorrow.
Are we learning something new? Again?
You know what? We might do. We might skip to 3.4. No, we won't either because we need that. Yes. Yes, you have to read in this section and watch the video or something. It's implicit, or come in and I can go through it with you, but it's implicit differentiation is what it's called.
Okay.
It probably takes a little more time than what we have right now to talk about.
Okay.
But,
Would I be able, I don't know if this would work out for me, but would I be able to come in tomorrow morning and get it at least started?
yeah. Well, you know what? I might be able to show you. I might be able to show you some basics of it right now, and then if you're still not sure,
Can I get it on that too?
you're gonna be gone tomorrow. Okay, let's do that. Let's just do that right now. Somewhere. In a whole pile of scratch paper. Well, we'll just use this.
that I created. What?
All right. All right. If I have, if you want to write this down, if I have f of x to the third power, this is based on what we just learned, what we just talked about. If I have f of x to the third power and I want to do that derivative, what would I do?
You could do the quotient, the product 3 times.
Well, right, but that would be that wouldn't be fun. The new one we learned, the chain rule, right? You just got this on the inside, that's the outside, right?
Right.
So we would do what? We would bring the 3 down in front. We would leave the f of x alone to the second power
And then you would do the derivative for the inside.
times the derivative inside, which would be f prime of x, right? Now that makes perfect sense based on what we learned today, right? Okay, now you know that when we use function notation, if I write like f of x equals sine x, that's really the same thing as saying y equals sine x, right? F of x and y, those are the outputs. Same thing. Okay. Well, if I wrote a function, if I wrote something as y cubed, and I said